Have you ever walked into a restaurant, ordered a meal, and then been told to head to the kitchen to prepare it yourself? Not only that, you're expected to operate the machinery, follow health and safety regulations, and make sure the kitchen stays spotless. Sounds ridiculous, right?
Yes, yet this is exactly the problem many developers face when trying to deploy their applications. They're expected to understand infrastructure, configure environments, manage deployments, and ensure that everything is secure and compliant before a single user sees their code. Now, you must all be sitting here thinking like, Nick, Andre, what the hell does a Rockamama's menu have to do with a talk on engineering? Well, what I want you all to do is keep this menu in the back of your minds for the remainder of this talk.
Platform engineering, a restaurant for developers. It's a model where developers are offered a curated menu of well-crafted solutions to run and host their applications. Instead of reinventing the wheel every time, they can focus on what they're actually meant to do. Write code that delivers value. The platform team handles the rest: security, scalability, compliance, and infrastructure behind the scenes.
Let's rewind to the early days of software development. Back then, deploying your application often meant writing code, testing it locally, and then manually uploading it to a central server or mainframe. Collaboration was difficult, and version control, if it existed at all, was a crude and error-prone process. Developers really had no easy way to track their changes or to safely work together. Everyone had their own systems, and integrating changes was a fragile and frustrating process. So quick show of hands, who of the older people in the audience here today maybe once had the job title of a systems administrator or operations? Okay, there's a couple. Well, back in these people's days, they used to actually type out these things called commands into a terminal to make a computer do things.
So, welcome to Yellow Ink. It's the year 1995. Nick is a new joiner in our company, and I would like him to deploy our code to production. It's well documented, and it should go off without a hitch. So, what can go wrong, right?
So anyways, I've been at this company for like 2 weeks, and I'm not feeling very confident, but you know what? I trust Andre. I trust it's a simple process. So I go ahead, I read through the documentation, and as Andre promised, it's a simple two-step process. One, I SSH into the jump box, which I've already done. And two, I run the infamous deploy.sh script. Making sure for no typos, of course, and press enter. I mean, it's doing something at least. Okay, and the command exited. But did that actually work? Well, I remember from my days in university that I can run a Unix command to check. So I run echo, and I see the 1. If I'm understanding correctly, that's not good. Should be a 0. So anyways, I reach out to Andre, and I'm like, listen, Andre, the deployment I ran didn't work.
Nick, what script did you run?
Deploy.sh, the one from the docs.
Ah, yes, I remember now. We made changes to the database, and I had to create a new script. If you do a simple ls, you'll find the correct one.
So anyways, I check. Oh, okay. So there's a couple of scripts here, but there's this obvious one sitting here. Deploy that works, .sh. You know, who am I to argue with something as appropriately named? So without thinking twice, I type out the command, tab complete and all, and press enter. Fingers crossed, things work this time. I mean, the deployment failed. Maybe I should reach out to Andre again. Ooh, that's definitely not right.
Well, they say you haven't lived until you've taken down production.
Let's revisit how the software world has evolved to make our lives as software developers easier. But before that, I'm going to run a script that's very appropriately named for later.sh. And as the name says, it's for later. So we'll come back to this later. Then in 2005, something groundbreaking happened. Git was introduced, and it changed everything. Suddenly, developers could work collaboratively with confidence. They could branch, merge, track, and roll back changes with ease. This was a huge leap forward. Finally, version control no longer stood in the way of productivity. But as teams began moving faster, the bottleneck shifted. Now the problem wasn't code collaboration. It was everything that happened after the commit.
That's where tools like Jenkins stepped in, automating builds and deployments. Jenkins helped bridge the gap between writing code and getting it in production, automating what used to be a slow, error-prone manual process. But this came with a trade-off. Developers now had to write and maintain complex pipeline definitions. A new category of knowledge was introduced, CI/CD infrastructure. Suddenly, being a good developer wasn't good enough. You also needed to know how to maintain build servers, script jobs, and even debug YAML.
And even if your code was built and deployed correctly, there was really no guarantee it would run as expected. Enter the infamous "it works on my machine" phrase. I know we've all at least once heard before in our lifetimes. So, differences in operating systems, dependencies, and systems architecture often made it difficult to ensure consistency between dev and production environments. Java attempted to solve this problem with the JVM, with the write once, run anywhere paradigm. And then later, Docker arrived with a more generalized solution, containerization. Now, developers could package their applications with their environments, leading to more consistent and reliable deployments. But again, another layer of tooling has been added, and with it, more cognitive load.
All of this code, now reliably built and containerized, still had to run somewhere. Initially, applications were deployed to physical servers, often hosted on-premise. Mainframes and later company-owned data centers dominated. They required massive upfront investment, ongoing maintenance, and a team of experts just to keep the lights on. Hosting was expensive, rigid, and difficult to scale. The rise of cloud computing promised to fix that. The idea was simple: stop managing hardware and rent compute power on demand. You only pay for what you use, and someone else takes care of the underlying infrastructure. On paper, it seems perfect. Cloud offers scalability, flexibility, and lower operational burden. In reality, however, developers now understand a vast ecosystem of services, configurations, and pricing models. The simplicity of pushing code had been replaced by learning IAM roles, VPC configurations, auto-scaling rules, service quotas, and much more.
So, while each innovation solved real problems, Git for collaboration, Jenkins for automation, Docker for environment consistency, and the cloud for scalability, they also added new layers of complexity. Developers went from coding to becoming part-time infrastructure engineers, security analysts, and cost managers. We've traded in one set of challenges for another, and the overhead keeps growing.
To deal with the rising complexity, many companies turn to DevOps, embedding a DevOps engineer into every team. These engineers became responsible for setting up pipelines, managing infrastructure, and helping developers get their code into production. But instead of streamlining delivery, this often created new silos. Developers now had to rely on a DevOps intermediary, someone they had to wait on, coordinate with, or in the worst case, even train. It's like running a restaurant where every table brings their own cook into the kitchen. Everyone is trying to prepare the same dish, but with different recipes, skills, and tools. Some cooks are fast, some are slow, and some are quite unsure where the kitchen is to begin with. The kitchen turns chaotic, quality suffers, and the outcome varies wildly. Plus, cooks are expensive, and not all of them are five-star chefs.
Over the years, we've tried to solve the challenges of software delivery with powerful tools and cultural shifts. From Git to CI/CD, containerization to the cloud, and DevOps practices. Each step brought meaningful improvements, but also added new layers of complexity and responsibility for our developers. We moved from mainframes to the cloud, but now we expect every developer to be a part-time coder, part-time infrastructure expert. DevOps aimed to bridge this gap, but it often ended up creating new silos, with each team bringing their own cook into the kitchen, leading to inconsistent outcomes, duplicated efforts, and rising costs.
This is the world platform engineering was born to fix. It's not just about automation. It's about crafting well-designed internal tools and services that developers can use without needing to understand every layer beneath them. Think of an early example like Heroku. Push your code and the platform takes care of the rest.
In companies, platform teams serve the same purpose. They are like expert chefs who craft high-quality, reliable dishes without expecting diners to understand the intricacies of every technique or ingredient. Similarly, platform teams design secure and reliable infrastructure components and deployment pipelines that developers can easily consume, like ordering from a well-curated menu, so they can focus on building features, not managing the kitchen. Instead of expecting every engineer to be an expert in security, cloud, and infrastructure, platform engineering provides them with guardrails and golden paths, predefined reliable ways to build and ship software. This approach accelerates development, reduces errors, and significantly improves the overall developer experience. It's not about restricting freedom, it's about removing friction so developers can focus on what they do best, which is creating impactful, high-quality software applications.
Deploying code should be as effortless as ordering a pizza on Uber Eats, right? Just a few taps and your meal is on its way. Developers shouldn't have to worry about provisioning infrastructure, configuring the network, or securing the environment every time they ship code. With platform engineering, the complexity is handled behind the scenes. So, delivering software becomes as smooth and predictable as a hot pizza showing up at your door.
So up to this point, you're all probably curious as to what platform engineering actually is. It's surely not about cooking meals, although the analogy isn't far off. Platform engineering is the practice of designing and building an integrated set of tools, processes, and environments that enable developers to build, deploy, and maintain their applications more efficiently. It involves creating and managing internal platforms that automate repetitive tasks, provides reusable components, and streamlines the overall software development lifecycle. Platform engineers focus on improving developer productivity by offering self-service capabilities, standardized workflows, and scalable infrastructure, allowing developers to focus on writing code and solving business problems rather than dealing with operational complexities. So this reference architecture shows the different components that might form part of your platform. At the heart of it is the platform orchestrator, the head chef of the kitchen, making sure that all the different technologies works together harmoniously. Now, this reference architecture looks good on paper, but you're all probably thinking, what actual technologies do I need to build this? Well, if you've ever had a conversation with a platform engineer like Andre and myself, chances are we've mentioned one specific tool that has become absolutely central to modern platforms.
Kubernetes. Now, many of you are probably thinking, a container orchestrator for platform engineering? And that's exactly the misconception we need to address. Yes, Kubernetes orchestrates containers, but that's just scratching the surface. Most people mistakenly see Kubernetes as just something that runs my containers. But it's so much more than that. And here's how we really see Kubernetes. It's a unified, extensible cloud-native API that happens to come with a container orchestrator built in. When we shift our mindsets to see Kubernetes as an extensible API first, we unlock the incredible possibility for building scalable, production-ready internal developer platforms.
So, who has seen this beautiful masterpiece over here before? So here's a quick pro tip if you want to make your LinkedIn profile really dope. Just close your eyes and start throwing some dots at this. And wherever that lands, you take that, you install that into your Kubernetes cluster, and that's good for like a 20% pay increase, minimum. Well, when we went about designing and building our platforms, we did exactly that. We just picked some random technologies off of this board, installed it into our Kubernetes cluster, and just like that, we have a platform, right?
No, of course not. We actually identified specific tools in this landscape that are fit for purpose and provided the functionality we needed to bring our platform vision to life. But to understand why we need a platform in the first place, let's step into the shoes of a developer trying to build something simple. Because what starts as a simple requirement quickly becomes an epic journey of complexity. Think of it as a developer's technical odyssey, where every simple feature leads to 10 more challenges they never saw coming.
Let's revisit our restaurant example. Business is booming, and we decide it's time to create a website where customers can order meals online and make reservations. Sounds simple enough, right? Well, let's see what this simple actually entails and why Odysseus would have understood our pain. We set sail on our journey with our requirements. For a functional application, we need a backend for business logic, a front end for user interactions, a database to store transactions, orders, reservation data, an IDP for user authentication and accounts, a message queue to track the placement of orders from the progress of orders from placement to delivery, and some basic monitoring to ensure that everything runs smoothly.
These are straightforward requirements for any modern web application. As the good developers, we start coding and use Git to track our changes. So far, so good. Nothing out of the ordinary. Then we hit our first roadblock. Where do we host all of this? After some research, Kubernetes seems like it will fit our purpose. But we lack on-premise expertise, so we chose to go with a cloud offering, Amazon EKS, our first detour from the simple path home. To set up EKS, we first need networking. And not just any networking, we need security best practices. Like Odysseus navigating between Scylla and Charybdis, one wrong move and we're vulnerable. With the networking configured and the basic cluster up and running, we realize we still don't have a single line of application code running. Kubernetes needs containers, so we Dockerize our code. But where do we store all of it? Enter Amazon ECR. Another island we need to conquer. Now, theoretically, we can deploy, but we need all those YAML definitions. Of the manual deployment proves as treacherous as a Cyclops caves, we use CI/CD to automate our way out of it. Great, we've got code running in our cluster, but like Odysseus, we're still far from home. Remember those original requirements? We still need to set up the IDP, the database, the messaging queue, and storage. All of these tools come with their own complexities, like VPC configurations, IAM roles, and much more. To manage all of this, we use Crossplane. All of this to realize we're still sailing blind without any observability. Enter the Grafana stack, adding more crew to our already overburdened ship. The sobering reality is, 6 months later, we finally have the infrastructure supporting our simple requirements. Our developers feel like they've been wandering the sea of infrastructure for decades. But here's the problem. Our clients don't interact with our infrastructure. They interact with our application. While we've been battling the sea of monsters and infrastructure complexity, we've lost precious time we could have been spent building features that actually drive value. We've lost sight of our Ithaca. The value isn't in conquering every technical challenge. It's in delivering the application that serves our customers.
The goal is simple. Let developers do what they do best. Build great applications, while the platform team handles the operational complexities, like having a goddess safely guiding you home. Those original requirements, well, they should be as simple as clicking a few buttons or writing a few lines of configuration, not a 6-month epic battling a many-headed infrastructure hydra, where solving one problem spawns 3 more. This is exactly what platform engineering delivers, turning that developer odyssey into a straightforward journey home, with all the monsters already tamed and the route clearly mapped.
In the end, developers should only need to focus on this. The rest should be handled by the platform behind the scenes, leaving developers free to focus on what they were meant to do, developing code that drives business value.
So guys, it's 2025, which means there's just one thing we haven't spoken about yet today. Any guesses? Yes, it's AI, of course. So naturally, when designing and building our platforms, we've asked ourselves, how can we leverage the current trends of agentic AI technologies out there to add AI capabilities to our platform stack? Well, we've already established that we have most of our platform's complexity hidden away behind the unified Kubernetes API. And unless you've been living under a rock the past year, open source technologies or standards like the Model Context Protocol have emerged, which allows us to very simply give our AI agents access to our platform's APIs.
At its core, platform engineering is about focus. Developers should be focused on building their applications, not managing auxiliary concerns like the infrastructure, security, and compliance. By shifting that burden to a dedicated platform team, we enable developers to move faster, safer, and with more confidence. To wrap things up, we've seen how every stage of software evolution has brought us powerful tools, but also more complexity. Platform engineering is our opportunity to reverse that trend by building developer-centric experiences that abstract away the noise. Now, instead of just talking about it, let's see what it actually feels like. Nick will walk you through a live demo that showcases how a well-designed internal platform empowers developers to go from writing code to production without touching a single piece of infrastructure.
So for today's demo, I've brought with a box. And just like Brad Pitt in the movie Seven, I'm sure you're all curious as to what's in the box. Well, actually, it's actually nothing major, but I'm actually going to show you guys. It's actually just hats. And every hat has a label on it, so I'm going to read them out quickly. So this one says DevOps. This one says Cloud Engineer. This one says Security. And this one says Developer. So for today's demo, I'm going to be channeling my inner developer. And as a matter of fact, I don't need this. So for today's demo, we'll be deploying a basic Next.js application that has an S3 bucket. And to do that, we'll be using a very appropriately named EscapeConf CLI. That is a custom-built CLI for our platform. Let's have a look at the menu for today. So we'll write the EscapeConf menu command. Now, I've already gone through the menu, and I know in order to create myself an application, I can run the EscapeConf app init command. Right, and as any good developer starting a project for the first time, we'll have to give the project the name of Hello World. Select Next.js and say confirm. So let's have a look at what the EscapeConf app init command has actually created for us. At first glance, you'll see it's nothing more than a basic Next.js scaffolded application. Nothing fancy. Also notice that there's not a single line of Terraform or any ISC or a single line or a single Docker file in this project. It seems to only be the business logic, except for this one specific file. Let me give you a quick rundown of what SCORE is. SCORE is an open source workload specification that was donated to the Cloud Native Computing Foundation. Why would we want to use it? Well, it prevents us as platform engineers from reinventing the wheel by defining our own workload specification that is specific to our platform. Rather than writing our own specification, we just use the specification, and as platform engineers, all we have to do is write an implementation that is specific to our platform. But this implementation is hidden away from developers inside the platform. Let's quickly have a look at what's in the file. First, we have the name of the application, some environment variables the application should run with, ports the application should listen on, and resources the application might depend on. For example, DNS entries, routes, S3 buckets, databases, message queues, just to name a few. For the purposes of today's demo, we'll be creating or adding a basic S3 bucket to our application. And to do that, it's as simple as adding 2 lines to this file, which I'm going to do now. Right, simple. I didn't have to touch a single AWS console or write a single line of Terraform, just a 2-liner change to the SCORE file. For the demo purposes, I will also add an environment variable called bucket name, which will equal the value of the bucket that the platform will create for us. And I do that by telling my platform, whatever the bucket's name is that you're going to create, set an environment variable called bucket name equal to that bucket's name. Right, at this point, we should probably start writing some business logic, but we'll probably skip over that for today's demo and just go straight to deploying our application. And to do that, it's as simple as running one command. The escape conf app launch command. So what's happening now is we're telling our platform, here is my application source code, please go and deploy it for me, with honoring the contents of the score file. We'll also see now that there's some logs getting streamed back remotely from the platform. In other words, everything is running remotely on the platform. Nothing is happening locally. While that's happening, let's have a look at what's actually happening in the background. From the developer's perspective, we have a single score.yaml file and our business logic open in VS Code. Consider the score.yaml file as being our filled-in Rockamama's menu and the CLI as the waiter that takes our order. When we ran the escape-conf app launch command, two things happened. One, our application source code was uploaded as an OCI artifact to an ECR repo, and two, a single API call was made to our platform's API. In plain English, we were telling our platform, here is my application source code and the recipe on how to deploy it. Do what you have to get my application deployed and running with all the necessary resources and configurations. Great. At this point, we can consider our application or our order as being placed. But let's actually have a look at what's going on inside the kitchen to get our meal prepared. First, the platform kicks off a multi-step Argo workflow, which will first trigger a cloud-native build pack build of our application source code and push the resultant build container image to a separate ECR repo. Next, let me actually quickly give you a rundown of what Cloud Native Build Packs is. Cloud Native Build Packs is an open source technology that was created over Heroku. It allows us to build container images without needing a Docker file, which I think is really cool. Great. Once we have our application source code built and pushed as a container image, we need to deploy it. And for that, we'll follow a GitOps-based deployment mechanism, where the platform will kick off a new workflow step, which will take as input our score.yaml file and our previously pushed container image and generate raw Kubernetes manifests that is pushed to a GitOps repository. After that, Argo CD picks up the manifests and syncs them up into our cluster. At this point, Crossplane picks up our cloud-specific resources and creates things like an IAM role and an S3 bucket. Finally, Knative deploys our previously pushed container image, sets up all the necessary networking configurations, and hooks up our workload to the previously created cloud resources. Finally, our platform responds with the URL of our deployed application. Now, this might look complex at first, but remember, all the developer sees is this. In other words, platform engineers walk so developers can run. So let's see how far our application is with deployment. Okay, it's almost done. I'm just going to have a water. "100 milliseconds does make a difference."
Nick, am I right on saying we did all of this by simply just extending the Kubernetes API?
Yes, correct. So we've hidden away most of the complexity of all those tools we've described before behind the unified Kubernetes API. In other words, we just had to make one API call to get our application deployed. Also, no Docker files, no infrastructure as code, just a single score.yaml file and our business logic. I don't think it gets any simpler than that. Also notice throughout this entire flow, I didn't touch a single AWS console, run a single kubectl command. In fact, I couldn't even care less where it's running. Right, so our application is deployed. Let's see if that actually worked. Great, app's running. Let's actually look if the database was also created for us. So you'll see over here, 45 seconds ago, our bucket was created. Right. Now, if you remember correctly, previously in this talk, we ran the forlater.sh script, and now is later. So let's have a look at what actually happened. So we've deployed an application called Speakers, which is myself and Andres per attempt at trying to replicate the speakers page from the EscapeConf website. It's written in Next.js, and it uses a database to store the information on the speakers and a bucket to store the information of the speakers' profile pictures. Let me quickly show you how the score.yaml file for this application looked. As you can see, it's not much different from the one we previously had. The only addition is we've added a database on line 23 and 24, and we've set a DB connection string environment variable that is dependent on the obviously created database's credentials. It's as simple as that. And then we ran the EscapeConf app launch command. Right. Let's add a speaker to our clone version of the Escape website. I'll call him John Doe. He'll be an oxygen thief at Earth. I'm too lazy to think of one. And he'll just be a chill guy.
So Nick, we've mentioned AI in our talk, but I've yet to see anything.
Yes, exactly, Andre. So rather than connecting to the database directly or going into the AWS console and checking out the buckets, let's actually use AI to investigate how our system reacted to me adding this new user. And for that, we'll go back to our EscapeConf CLI and run the EscapeConf copilot command. So that opens up a chat with a remote agent or agents that are running in our platform that have an MCP server so that the agents can get context of our platform's specific resources. Right. So I'll ask it, my friend, you list me my apps, databases, and buckets, please. Let's hope that works. Great. Seems to have returned the right thing. I'm actually interested to see what's inside the speakers database. So I'm going to ask it, can you list me the tables in the speakers DB? Great. Finally, I want to see the information in this table. So I'm going to ask it, show me the rows of this table. Great. I'm sure, okay, I'm actually just going to quickly ask it to give me more information about John Doe.
Nick, I'm quite sure the audience would also like to see what John Doe actually looks like.
Yeah, good point. Let me check.
Yeah, sometimes a bit, a bit of prompt engineering helps a bit.
Let's try that again. These AI aren't perfect, by the way. Anyways, I'm just going to show you what he looks like. It didn't work today.
And we tested it like a million times, but just shows you. real men test in production.
Anyways, thank you guys for joining us for today's talk. Myself and Andrew are really happy to share our passion we have for platform engineering and a whole bunch of cloud native technologies and show how we can build internal developer platforms and incorporate AI capabilities into them. Thanks.
Yeah, we'd love it if you guys got any questions for us.
Hi. How do you deal with developers that do want their own Docker files and want slight custom things in the recipes that you provide?
So, right, our job as platform engineers is to provide you with golden paths. You don't have to take that golden path or use that recipe, right? You can do whatever you want. But really where we know that our product, because we're building a platform as a product, is working, is if a developer would rather use our platform than doing the things manually. In other words, creating the Docker file, setting up the pipeline himself, setting up the Terraform to deploy his cloud resources, right? Does that answer your question? Eventually, we want to get to a point where everybody wants to use the platform.
How do you manage things like scope and access control when everything is served from a code-based perspective where I as an engineer can best pretend I just want to drop the prod DB today and I remove it from my score resources?
Yes, exactly,
How do you
right?
handle
So like we previously said, our whole platform is built and extends the Kubernetes API, right? If you've ever worked with Kubernetes, it has RBAC mechanisms built in for every specific API endpoint you have, right? So that can be like, we had a custom database endpoint on our API. You give RBAC access with OIDC login. That can be Azure AD, Cognito, whatever, right? You log into the platform with that identity provider, which I didn't show in the demo. And then from there, when you're logged in, you would probably be part of a certain group and you get certain levels of access, maybe only a reader role or a writer role, or maybe you only have access to specific APIs. In other words, you might only be able to deploy apps, but not be able to delete databases or delete buckets, right? Yeah.
Hi, guys. As a product owner, why would I do this instead of buying something off the shelf, like Harness, for example?
So in larger companies, like we said, there's a bunch of technologies floating around, right? So you can think of one company might be using GitHub, another might be using Azure DevOps, right? Then another company might be using AWS or Azure. They might be using Kubernetes. They might be using ECS. They might be using Jenkins for their ticketing system or Azure DevOps boards for their ticketing system. So every company has different requirements. There isn't actually an offer out there that solves the challenges of all these different tools and incorporates them into one, right? Also, internal developer platform. The internal part of the word is very important because it's internal to the organization. It's not an external developer platform. Examples of external platforms are things like AWS and Azure, high fidelity platforms where you require a lot of knowledge, but they have the capabilities to, pretty much provide everybody in the world what they would want. But from AWS's perspective, we might only be using, 10 of the 400 odd services out there, right? So we don't care about the other 390. We only care about the first 10. And then we have to incorporate that with our GitHub, We have to incorporate that with our Jenkins. And yeah, you can't really generalize on that sort of thing because every company is different.
Thanks. What about vulnerability scanning and all that?
So there are tools out there that you can install into Kubernetes for runtime threat protection and image scanning, right? So Trevi is an example of something you can use to, before, when the image is built, before it's even deployed, going live, right? The one step where you're building the image, you can add an extra step in there that does the image scanning and, you know, prevents you from going on in the deployment when there's vulnerabilities detected in your source code. Also with cloud native build packs, that takes care of a lot of that because you can't introduce vulnerabilities in a Docker file, which a lot of people end up doing because they might end up running their containers as roots, might be adding a library that has a vulnerability or using a base image that, you know, has critical vulnerabilities in it. Yeah. And then runtime threat protection, you know, scanning things while they run live.
Thanks for the presentation. So I just want to ask, so is this type of a platform is a bit specialized where you need a platform team that can kind of build this?
Yes, exactly.
Out. So, or maybe a newer or a less experienced platform team, they might want to go with a solution out of the box, like let's build on AWS only. Where do you think is the line drawn between going with something existing versus spending the time on getting this? Because a solution out of the box might work for now, but as you build in more complexity or specialization, what your company wants, where do you guys think is that line drawn in time to build something with this rather than going with a more generalized platform?
The short answer is the scale of your organization. How many people, engineers are in your organization, right? If you have, let's say, 50 engineers, then AWS might be fine. But when you get to like hundreds of engineers, even thousands of engineers, then, you know, everybody, like Andre previously said in the talk, every business unit has their own DevOps person, and each of those DevOps people do things in a different way. I'm sure you've been at your client where you've gone to a different team and you're like, why are you doing things this way, right? They've reinvented the wheel. You're doing something a completely different way. Maybe they're using Lambda, you're using ECS or Kubernetes, right? And then at that point, everybody is doing their own thing. They're not following any standards. Again, onboarding new teams becomes a thing, right? When you're onboarding a new team, they have to go through that same procedure of getting a DevOps guy. Maybe he's skilled, maybe he's not. And then it takes like 6 months to get a new project on board. And if the organization is doing that a lot, then building a platform team or putting together a platform team, a team that is maybe 5 to 10 engineers dedicated to building this platform as a product for your organization. In other words, the clients of our product is the developers, the other developers in the business units, right? So you build features into your platform that actually solve problems that the other developers using your platform would like to have.
Yeah, the first sign you see of that generally is when teams start building silos. Each team starts doing their own thing because your core components simply can't meet the requirements they needed. It's usually an indicator of it.
Nicholas, we have the last question there on the screen for the online audience.
I'd say just go and read up all the case studies on the platformengineering.org website on companies that have actually adopted it. One of the biggest companies that have adopted the whole platform engineering paradigm is Spotify. They found a lot of success into building an internal platform for the entire organization. As a matter of fact, the one tool we had up there called Backstage was actually created over at Spotify and later donated again to the Cloud Native Computing Foundation. Oh, thanks everyone.